Chapter 3 of Gardening Without Irrigation. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Betsy Bush, September 2009. Gardening Without Irrigation, or Without Much Anyway, by Steve Solomon. Chapter 3. Helping Plants to Need Less Irrigation. Dry though the maritime Northwest summer is, we enter the growing season with our full depth of soil at field capacity. Except on clayey soils in extraordinarily frosty, high-elevation locations, we usually can till and plant before the soil has had a chance to lose much moisture. There are a number of things we can do to make soil moisture more available to our summer vegetables. The most obvious step is thorough weeding. Next, we can keep the surface fluffed up with a rotary tiller or hoe during April and May to break its capillary connection with deeper soil and accelerate the formation of a dry dust mulch. Usually, weeding forces us to do this anyway. Also, if it should rain during summer, we can hoe or rotary till a day or two later and again help a new dust mulch to develop. Building bigger root systems. Without irrigation, most of the plant's water supply is obtained by expansion into new earth that hasn't been desiccated by other competing roots. Eliminating any obstacles to rapid growth of root systems is the key to success. So keep in mind a few facts about how roots grow and prosper. The air supply in soil limits or allows root growth. Unlike the leaves, roots do not perform photosynthesis, breaking down carbon dioxide gas into atmospheric oxygen and carbon. Yet, root cells must breathe oxygen. This is obtained from the air held in spaces between soil particles. Many other soil-dwelling life forms, from bacteria to moles, compete for this same oxygen. Consequently, soil oxygen levels are lower than in the atmosphere. A slow exchange of gases does occur between soil air and free atmosphere, but deeper in the soil there will inevitably be less oxygen. Different plant species have varying degrees of root tolerance for lack of oxygen, but they all stop growing at some depth. Moisture reserves below the root's maximum depth become relatively inaccessible. Soil compaction reduces the overall supply and exchange of soil air. Compacted soil also acts as a mechanical barrier to root system expansion. When gardening with unlimited irrigation, or where rain falls frequently, it is quite possible to have satisfactory growth when only the surface 6 or 7 inches of soil facilitates root development. When gardening with limited water, China's the limit, because if soil conditions permit, many vegetable species are capable of reaching 4, 5, and 8 feet down to find moisture and nutrition. Evaluating potential rooting ability. One of the most instructive things a water-wise gardener can do is to rent or borrow a hand-operated fence-post auger and bore a 3-foot deep hole. It can be even more educational to buy a short section of ordinary water pipe to extend the auger's reach another 2 or 3 feet down. In soil free of stones, using an auger is more instructive than using a conventional post-hole digger or shoveling out a small pit, because where soil is loose, the hole deepens rapidly. Where any layer is even slightly compacted, one turns and turns the bit without much effect. Augers also lift the materials more or less as they're stratified. If your soil is somewhat stony, like much upland soil north of Centralia, left by the Vashon Glacier, the more usual fence-post digger or common shovel works better. If you find more than 4 feet of soil, the site holds a dry gardening potential that increases with the additional depth. Some soils along the floodplains of rivers or in broad valleys like the Willamette or Skagit can be over 20 feet deep and hold far more water than the deepest roots could draw or capillary flow could raise during an entire growing season. Gently sloping land can often carry 5 to 7 feet of open usable soil. However, soils on steep hillsides become increasingly thin and fragile with increasing slope. Whether an urban, suburban, or rural gardener, you should make no assumptions about the depth and openness of the soil at your disposal. Dig a test hole. If you find less than 2 unfortunate feet of open earth before hitting an impermeable obstacle such as rock or gravel, Not much water storage can occur, and the only use this book will hold for you is to guide your move to a more likely gardening location, or encourage the house hunter to seek further. Of course, you can still garden quite successfully on thin soil in the conventional irrigated manner. Growing vegetables west of the Cascades will be an excellent guide for this type of situation. Eliminating plowpan. Deep though the soil may be, any restriction of root expansion greatly limits the ability of plants to aggressively find water. A compacted subsoil or even a thin compressed layer such as plowpan may function as such a barrier. Though moisture will still rise slowly by capillarity and recharge soil above plowpan, plants obtain much more water by rooting into unoccupied damp soil. Soils close to river or on floodplains may appear loose and infinitely deep, but may hide subsoil streaks of droughty gravel that effectually stops root growth. Some of these conditions are correctable and some are not. Plowpan is very commonly encountered by homesteaders on farm soils and may be found in suburbia too, but fortunately it is the easiest obstacle to remedy. Traditionally, American croplands have been tilled with the mold-board plow. As this implement first cuts and then flips a 6 or 7 inch deep slice of soil over, the sole, the part supporting the plow's weight, presses heavily on the earth about 7 inches below the surface. With each subsequent plowing, the plow sole rides at the same 7-inch depth, an even more compacted layer develops. Once formed, plowpan prevents the crop from rooting into the subsoil. Since winter rains leach nutrients from the topsoil and deposit them in the subsoil, plowpan prevents access to these nutrients and effectively impoverishes the field. So wise farmers periodically use a subsoil plow to fracture the pan. Plowpan can seem as firm as a rammed earth house. Once established, it can last a long, long time. My own garden land is part of what was once an old wheat farm, one of the first homesteads of the Oregon Territory. From about 1860 through the 1930s, the field produced small grains. Another wheat became unprofitable, probably because of changing market conditions and soil exhaustion. The field became an unplowed pasture. Then, in the 1970s, it grew daffodil bulbs, occasioning more plowing. All through the 80s, my soil again rested under grass. In 1987, when I began using the land, there was still a 2-inch thick, very hard layer starting about 7 inches down. Below 9 inches, the open earth is soft as butter, as far as I've ever dug. On a garden-sized plot, plowpan or compacted subsoil is easily opened with a spading fork or a very sharp common shovel. After normal rotary tilling, either tool can fairly easily be wiggled 12 inches into the earth and small bites of plowpan loosened. Once this laborious chore is accomplished the first time, deep tillage will be far easier. In fact, it comes so easy that I've been looking for a custom-made fork with longer tines. Curing clay soils. In humid climates like ours, sandy soils may seem very open and friable on the surface, but frequently hold some unpleasant subsoil surprises. Over geologic time spans, mineral grains are slowly destroyed by weak soil acids and clay is formed from the breakdown products. Then heavy winter rainfall transports these minuscule clay particles deeper into the earth, where they concentrate. It is not unusual to find a sandy topsoil underlaid with a dense cement-like clay sand subsoil, extending down several feet. If very impervious, a thick, dense deposition like this may be called hardpan. The spading fork cannot cure this condition as simply as it can eliminate thin plowpan. Here is one situation where, if I had a neighbor with a large tractor and subsoil plow, I'd hire him to fracture my land 3 or 4 feet deep. Painstakingly double or even triple digging will also loosen this layer. Another possible strategy for a smaller garden would be to rent a gasoline-powered post-hole auger, spread manure or compost an inch or 2 thick, and then bore numerous almost adjoining holes 4 feet deep all over the garden. Clayey subsoil can supply surprisingly larger amounts of moisture than the granular sandy surface might imply, but only if the earth is opened deeply and becomes more accessible to root growth. Fortunately, once root development increases at greater depths, the organic matter content and accessibility of this clayey layer can be maintained through intelligent green manuring, postponing for years the need to subsoil again. Green manuring is discussed in detail shortly. Other sites may have gooey, very fine clay topsoils, almost inevitably with gooey, very fine clay subsoils as well. Though incorporation of extraordinarily large quantities of organic matter can turn the top few inches into something that behaves a little like loam, it is quite impractical to work in humus to a depth of 4 or 5 feet. Root development will still be limited to the surface layer. Very fine clays don't make likely dry gardens. Not all clay soils are fine clay soils, totally compacted and airless. For example, on the gentler slopes of the geologic old Cascades, those 500-million-year-old black basalts that form the Cascades foothills and appear in other places throughout the maritime Northwest, a deep friable red clay soil called, in Oregon, jori often forms. Jori clays can be 6 to 8 feet deep and are sufficiently porous and well drained to have been used for highly productive orchard crops. Water-wise gardeners can do wonders with joris and other similar soils, though clays never grow the best root crops. Spotting a likely site. Observing the condition of wild plants can reveal a good site to garden without much irrigation. Where Himalaya or evergreen blackberries grow 2 feet tall and produce small, dull-tasting fruit, there is not much available soil moisture. Where they grow 6 feet tall and the berries are sweet and good-sized, there is deep open soil. When the berry vines are 8 or more feet tall and the fruits are especially huge, usually there is both deep soil and a higher than usual amount of fertility. Other native vegetation can also reveal a lot about soil moisture reserves. For years I wondered at the short leaders and sad appearance of Douglas fir in the vicinity of Yelm, Washington. Were they due to extreme soil infertility? When I learned that conifer trees responded more to summertime soil moisture than to fertility, I obtained a soil survey of Thurston County and discovered that much of that area was very sandy with gravelly subsoil. Eureka! The Soil Conservation Service, SCS, a U.S. government agency, has probably put a soil auger into your very land or a plot close by. Its tests have been correlated and mapped. The soils underlying the maritime Northwest have been named and categorized by texture depth and ability to provide available moisture. The maps are precise and detailed enough to approximately locate a city or suburban lot. In 1987, when I was in the market for a new homestead, I first went to my county SCS office, mapped out locations where the soil was suitable, and then went hunting. Most counties have their own office. Using humus to increase soil moisture. Maintaining topsoil humus content in the 4 to 5% range is vital to plant health, vital to growing more nutritious food, and essential to bringing the soil into that state of easy workability and cooperation known as good tilth. Humus is a spongy substance capable of holding several times more available moisture than clay. There are also new synthetic, long-lasting soil amendments that hold and release even more moisture than humus. Garden books frequently recommend tilling in extraordinarily large amounts of organic matter to increase a soil's water-holding capacity in the top few inches. Humus can improve many aspects of soil, but will not reduce a garden's overall need for irrigation, because it is simply not practical to maintain sufficient humus deeply enough. Rotary tilling only blends amendments into the top 6 or 7 inches of soil. Rigorous double digging by actually trenching out 12 inches and then spading up the next foot theoretically allows one to mix in sufficient amounts of organic matter to nearly 24 inches. But plants can use water from far deeper than that. Let's realistically consider how much soil moisture reserves might be increased by double digging and incorporating large quantities of organic matter. A healthy topsoil organic matter level in our climate is about 4%. This rapidly declines to less than 0.5% in the subsoil. Suppose inches-thick layers of compost were spread and by double digging, the organic matter content of a very sandy soil were amended to 10% down to 2 feet. If that soil contained little clay, its water-holding ability in the top 2 feet could be doubled. Referring to the chart Available Moisture in Chapter 2, we see that sandy soil can release up to 1 inch of water per foot. By dint of massive amendment, we might add 1 inch of available moisture per foot of soil to the reserve. That's 2 extra inches of water, enough to increase the time an ordinary garden can last between heavy irrigations by a week or 10 days. If the soil in question were a silty clay, it would naturally make 2.5 inches available per foot. A massive humus amendment would increase that to 3.5 inches in the top foot or two, relatively not as much benefit as in sandy soil. And I seriously doubt that many gardeners would be willing to thoroughly double dig to an honest 24 inches. Trying to maintain organic matter levels above 10% is an almost self-defeating process. The higher the humus level gets, the more rapidly organic matter tends to decay. Finding or making enough well-finished compost to cover the garden several inches deep, what it takes to lift humus levels to 10%, is enough of a job. Double digging just as much more into the second foot is even more effort. But having to repeat that chore every year or two becomes downright discouraging. No, either your soil naturally holds enough moisture to permit dry gardening, or it doesn't. Keeping the subsoil open with green manuring. When roots decay, fresh organic matter and large, long-lasting passageways can be left deep in the soil, allowing easier air movement and facilitating entry of other roots. But no cover crop that I am aware of will effectively penetrate firm plowpan or other resistant physical obstacles. Such a barrier forces all plants to root almost exclusively in the topsoil. However, once the subsoil has been mechanically fractured the first time, and if recompaction is avoided by shunning heavy tractors and other machinery, green manure crops can maintain the openness of the subsoil. To accomplish this, correct green manure species selection is essential. Lawn grasses tend to be shallow rooting, while most regionally adapted pasture grasses can reach down about 3 feet at best. However, orchard grass, called coltsfoot in English farming books, will grow down 4 or more feet while leaving a massive amount of decaying organic matter in the subsoil after the sod is tilled in. Sweet clover, a biennial legume that sprouts one spring then winters over to bloom the next summer, may go down 8 feet. Red clover, a perennial species, may thickly invade the top 5 feet. Other useful subsoil busters include densely sown umbelliferae, such as carrots, parsley, and parsnips. The chicory family also makes very large and penetrating taproots. Though seed for wild chicory is hard to obtain, cheap varieties of endive, a semi-cultivated relative, are easily available, and several pounds of your own excellent parsley or parsnip seed can be easily produced by letting about 10 row feet of overwintering crops form seed. Orchard grass and red clover can be had quite inexpensively at many farm supply stores. Sweet clover is not currently grown by our region's farmers, and so can only be found by mail from Johnny's Selected Seeds. See Chapter 5 for their address. Poppy seed used for cooking will often sprout. Sown densely in October, it forms a thick carpet of frilly spring greens underlaid with countless massive taproots that decompose very rapidly if the plants are tilled in April before flower stalks begin to appear. Beware if using poppies as a green manure crop. Be sure to till them in early to avoid trouble with the DEA or other authorities. For country gardeners, the best rotations include several years of perennial grass, legume, herb mixtures to maintain the openness of the subsoil, followed by a few years of vegetables, and then back. See Newman Turner's book in More Reading. I plan my own garden this way. In October, after a few inches of rain has softened the earth, I spread 50 pounds of agricultural lime per 1,000 square feet and break the thick pasture sod covering next year's garden plot by shallow rotary tilling. Early the next spring, I broadcast a concoction I call Complete Organic Fertilizer. See Growing Vegetables West of Cascades or the Territorial Seed Company catalog. Till again after the soil dries down a bit, and then use a spading fork to open the subsoil before making a seedbed. The first time around, I had to break the century-old plow pan. Forking compacted earth a foot deep is a lot of work. In subsequent rotations it is much, much easier. For a couple of years, vegetables will grow vigorously on this new ground, supported only with a complete organic fertilizer. But vegetable gardening makes humus levels decline rapidly. So every few years I start a new garden on another plot and replant the old garden to green manures. I never remove vegetation during the long rebuilding under green manures, but merely mow it once or twice a year and allow the organic matter content of the soil to redevelop. If there ever were a place where chemical fertilizers might be appropriate around a garden, it would be to affordably enhance the growth of biomass during green manuring. Were I a serious city vegetable gardener, I'd consider growing vegetables in the front yard for a few years and then switching to the backyard. Having lots of space, as I do now, I keep 3 or 4 garden plots available, one in vegetables and the others restoring the organic matter content under grass. Mulching. Gardening under a permanent thick mulch of crude organic matter is recommended by Ruth Stout, see the listing for her book in more reading, and her disciples as a surefire way to drought-proof gardens while eliminating virtually any need for tillage, weeding, and fertilizing. I have attempted the method in both Southern California and Western Oregon, with disastrous results in both locations. What follows in this section is addressed to gardeners who have already read glowing reports about mulching. Permanent mulching with vegetation actually does not reduce summertime moisture loss any better than mulching with dry soil, sometimes called dust mulching. True, while the surface layer stays moist, water will steadily be wicked up by capillarity and be evaporated from the soil's surface. If frequent light sprinklings keep the surface permanently moist, subsoil moisture loss can occur all summer. So unmulched soil could eventually become desiccated many feet deep. However, capillary movement only happens when soil is damp. Once even a thin layer of soil has become quite dry, it almost completely prevents any further movement. West of the Cascades, this happens all by itself in late spring. One hot, sunny day follows another, and soon the earth's surface seems parched. Unfortunately, by the time a dusty layer forms, quite a bit of soil water can have risen from the depths and been lost. The gardener can significantly reduce spring moisture loss by frequently hoeing weeds until the top inch or 2 of earth is dry and powdery. This effort will probably be necessary in any case, because weeds will germinate prolifically until the surface layer is sufficiently desiccated. On the off chance it should rain hard during summer, it is very wise to again hoe a few inches to rapidly restore the dust mulch. If hand cultivation seems very hard work, I suggest you learn to sharpen your hoe. A mulch of dry hay, grass clippings, leaves, and the like will also retard rapid surface evaporation. Gardeners think mulching prevents moisture loss better than bare earth because under mulch the soil stays damp right to the surface. However, dig down 4 to 6 inches under a dust mulch and the earth is just as damp as under hay. And soil moisture studies have proved that overall moisture loss using vegetation mulch slightly exceeds loss under a dust mulch. West of the Cascades, the question of which method is superior is a bit complex, with pros and cons on both sides. Without a long winter freeze to set populations back, permanent thick mulch quickly breeds so many slugs, earwigs, and sowbugs that it cannot be maintained for more than 1 year before vegetable gardening becomes very difficult. Laying down a fairly thin mulch in June after the soil has warmed up well, raking up what remains of the mulch early the next spring, and composting it prevents destructive insect population levels from developing while simultaneously reducing surface compaction by winter rains and beneficially enhancing the survival and multiplication of earthworms. But a thin mulch also enhances the summer germination of weed seeds without being thick enough to suppress their emergence. And any mulch, even a thin one, makes hoeing virtually impossible, while hand weeding through mulch is tedious. Mulch has some unqualified pluses in hotter climates. Most of the organic matter in soil, and consequently most of the available nitrogen, is found in the surface few inches. Levels of other mineral nutrients are usually 2 or 3 times as high in the topsoil as well. However, if the surface few inches of soil becomes completely desiccated, no root activity will occur there, and the plants are forced to feed deeper in soil far less fertile. Keeping the topsoil damp does greatly improve the growth of some shallow-feeding species, such as lettuce and radishes. But with our climate's cool nights, most vegetables need the soil as warm as possible, and the cooling effect of mulch can be as much a hindrance as a help. I've tried mulching quite a few species while dry gardening, and found little or no improvement in plant growth with most of them. Probably the enhancement of nutrition compensates for the harm from lowering soil temperature. Fertigation is better all around. Wind breaks. Plants transpire more moisture when the sun shines, when temperatures are high, and when the wind blows. It is just like drying laundry. Windbreaks also help the garden grow in winter by increasing temperature. Many other garden books discuss windbreaks, and I conclude that I have a better use for the small amount of words my publisher allows me than to repeat this data. Bindakal Brooks, Winter Gardening in the Maritime Northwest, Sasquatch Books, 1989, is especially good on this topic. Fertilizing, fertigating, and foliar spraying. In our heavily leached region, almost no soil is naturally rich, while fertilizers, manures, and potent composts mainly improve the topsoil. But the water-wise gardener must get nutrition down deep, where the soil stays damp through the summer. If plants with enough remaining elbow room stop growing in summer and begin to appear gnarly, it is just as likely due to lack of nutrition as lack of water. Several things can be done to limit or prevent midsummer stunting. First, before sowing or transplanting large species like tomato, squash, or big brassicas, dig out a small pit about 12 inches deep, and below that blend in a handful or two of organic fertilizer. Then fill the hole back in. This double digging process places concentrated fertility mixed 18 to 24 inches below the seeds or seedlings. Foliar feeding is another water-wise technique that keeps the plants growing through the summer. Soluble nutrients sprayed on plant leaves are rapidly taken into the vascular system. Unfortunately, dilute nutrient solutions that won't burn leaves only provoke a strong growth response for 3 to 5 days. Optimally, foliar nutrition must be applied weekly or even more frequently. To efficiently spray a garden larger than a few hundred square feet, I suggest buying an industrial-grade 3-gallon backpack sprayer with a side handle pump. Approximate cost, as of this writing, was $80. The store that sells it, probably a farm supply store, will also support you with a complete assortment of inexpensive nozzles that can vary the rate of emission and the spray pattern. High-quality equipment like this outlasts many cheaper and smaller sprayers designed for the consumer market, and replacement parts are also available. Keep in mind that consumer merchandise is designed to be consumed. Stuff made for farming is built to last. Increasing soil fertility saves water. Does crop growth equal water use? Most people would say this statement seems likely to be true. Actually, faster-growing crops use much less soil moisture than slower-growing ones. As early as 1882, it was determined that less water is required to produce a pound of plant material when soil is fertilized than when it is not fertilized. One experiment required 1,100 pounds of water to grow 1 pound of dry matter on infertile soil, but only 575 pounds of water to produce a pound of dry matter on rich land. Perhaps the single most important thing a water-wise gardener can do is to increase the fertility of the soil, especially the subsoil. Poor plant nutrition increases the water cost of every pound of dry matter produced. Using foliar fertilizers requires a little caution and forethought. Spinach, beet, and chard leaves seem particularly sensitive to foliars, and even to organic insecticides, and may be damaged by even half-strength applications. And the cabbage family coats its leaf surfaces with a waxy, moisture-retentive sealant that makes sprays bead up and run off rather than stick and be absorbed. Mixing foliar feed solutions with a little spreader sticker, safer soap, or if bugs are also a problem, with a liquid organic insecticide like Red Arrow, a pyrethrum rhododendron mix, eliminates surface tension and allows the fertilizer to have an effect on brassicas. Sadly, in terms of nutrient balance, the poorest foliar sprays are organic. That's because it is nearly impossible to get significant quantities of phosphorus or calcium into solution using any combination of fish emulsion and seaweed or liquid kelp. The most useful possible organic foliar is half to 1 tablespoon each of fish emulsion and liquid seaweed concentrate per gallon of water. Foliar spraying and fertigation are 2 occasions when I am comfortable supplementing my organic fertilizers with water-soluble chemical fertilizers. The best and most expensive brand is Rapid Grow. Less costly concoctions such as Peter's 20-20-20 or the other Grows don't provide as complete trace mineral support or use as many sources of nutrition. One thing fertilizer makers find expensive to accomplish is concocting a mixture of soluble nutrients that also contains calcium, a vital plant food. If you dissolve calcium nitrate into a solution containing other soluble plant nutrients, many of them will precipitate out because few calcium compounds are soluble. Even Rapid Grow doesn't attempt to supply calcium. Recently, I've discovered better quality hydroponic nutrient solutions that do use chemicals that provide soluble calcium. These also make excellent foliar sprays. Brands of hydroponic nutrient solutions seem to appear and vanish rapidly. I've had great luck with Dynagrow 795. All these chemicals are mixed at about 1 tablespoon per gallon. Vegetables that like foliars: asparagus, carrots, melons, squash, beans, cauliflower, peas, tomatoes, broccoli, Brussels sprouts, cucumbers, cabbage, eggplant, radishes, kale, rutabagas, potatoes. Don't like foliars: beets, leeks, onions, spinach, chard, lettuce, peppers. Like fertigation: Brussels sprouts, kale, Savoy cabbage, cucumbers, melons, squash, eggplant, peppers, tomatoes. Fertigation every 2 to 4 weeks is the best technique for maximizing yield while minimizing water use. I usually make my first fertigation late in June and continue periodically through early September. I use 6 or 7 plastic 5-gallon drip system buckets, see below, set one by each plant, and fill them all with a hose each time I work in the garden. Doing 12 or 14 plants each time I'm in the garden, it takes no special effort to rotate through them all more or less every 3 weeks. To make a drip bucket, drill a 3/16 inch hole through the side of a 4 to 6 gallon plastic bucket about 1/4 inch up from the bottom, or in the bottom at the edge. The empty bucket is placed so that the fertilized water drains out close to the stem of a plant. It is then filled with liquid fertilizer solution. It takes 5 to 10 minutes for 5 gallons to pass through a small opening, and because of the slow flow rate, water penetrates deeply into the subsoil without wetting much of the surface. Each fertigation makes the plant grow very rapidly for 2 to 3 weeks, more, I suspect, as a result of improved nutrition than from added moisture. Exactly how and when to fertigate each species is explained in Chapter 5. Organic gardeners may fertigate with combinations of fish emulsion and seaweed at the same dilution used for foliar spraying, or with compost manure tea. Determining the correct strength to make compost tea is a matter of trial and error. I usually rely on weak Rapid Grow mixed at half the recommended dilution. The strength of the fertilizer you need depends on how much and deeply you placed nutrition in the subsoil. End of Chapter 3.